So I want to start off by asking you to think about statements about probabilities and what they mean and how we can get our hands on them. So, I could ask you, what is the probability that if I flip a fair coin 16 times, I get exactly 19 heads? And this is a very concrete question. There's, different methodologies you could employ to answer this question. We've got, a very simple mathematical model for this physical process. We've got, like a Bernoulli random variable. And so you could just sit down and you could compute this in closed form. It'd be like a simple exercise in an undergraduate probability course. Or this is something that you could just, if given enough patience and time, empirically estimate. You could perform the experiment repeatedly. And the nice thing about this setting is the mathematical model maps very closely onto, it's a very good model for the physical world. And so if you did this experiment for long enough, it would agree very closely with the with the answer you got from the mathematical model. Okay, so this is sort of a good case. Now, there are other statements or questions that we can attach probabilities to, and people do, that are more difficult to get our hands on. So for example, you could ask, what is the probability that Canada will join the US as the 51st state before July? And this is a question that people do ask and bet money on. This is a screenshot from Polymarket. This was from right after the inauguration. I think the probability is a little lower now. But okay, like, you can think about what it would mean to believe that this statement has a 3% chance of being true. Certainly, we have no mathematical model that we believe sort of comports tightly enough with reality that you could sit down and compute this in closed form and have any faith that you were right. And, like, conceivably, you could have in your mind, like, a model of the universe that makes it philosophically coherent that an event like this has some probability that is not either 0% or 100%. Maybe you think the universe is probabilistic, and if I run it from the current starting conditions to the end of July over and over and over again, that, in roughly 3% of those outcomes, will Canada join the US as the 51st state? Maybe. But certainly, this is not an experiment that we can run. Okay, so we speak of probabilities even for things that we have no mechanism for estimating, either mathematically or empirically, in the way that we do things like coin flips. And, it sort of gets even worse than that. Like, people want to attach confidence scores to outputs that may or may not be factual from, language models. So for example, I could ask the question, I could say, well, look, ChatGPT tells me that the leading cause of death globally in children under 5 years old is diarrheal diseases. What is the probability that that is correct? And this one, unlike, will Canada become the 51st state before July? This one's not even a question about the future. Like, this one has an answer. Like, and I could find out the answer by, like, going to Wikipedia. Okay, so like, it's not even exactly philosophically coherent to believe that this has a 72% chance of being correct. Like, if I went to Wikipedia, I would learn either that it was right or wrong. Nevertheless, like, attaching confidence scores that seem to have probabilistic semantics to language models, well, maybe that would be useful. But, like, we need to figure out exactly what we mean here and useful how. So let's think about what we want from probabilities. Like, why do we want probabilities in the first place? So here's, like, a common scenario that is, maybe a little bit of a fiction, but let's go with it. Let's say that the observations that we make are governed by some distribution over feature and label pairs. And we see features, and we care about the labels insofar as they inform what action we want to take. There's something we want to do in the world, and the outcome of that thing that we do and how happy we correspondingly are depends on what the label is, but we don't know yet what the label is. That's the difficulty and the reason we want to predict the label so that we can take the action. Now, for all sorts of tasks, it turns out that the conditional distribution, conditional on the features of the label, would be a sufficient statistic for us to accomplish the task. For example, anytime we've got like a well-defined utility function as a function that tells us how happy we are as a function of the action we take and the label that's realized, and we care about maximizing the expected utility, or, by the way, minimizing expected loss. This covers all of supervised learning, essentially. If we knew the distribution on the labels, given all of the features we've seen, then we'd be in business. We could just sort of straightforwardly solve this optimization problem and figure out the best prediction or the best action. Okay, that would be great. But there's an immediate problem that hopefully some of these examples have put in your mind. First of all, these conditional probabilities might not even really exist in any useful form, right? They might be, for example, 0 or 1, like in the LM scenario, and difficult to, and therefore sort of inaccessible unless we have perfect prediction. Or maybe there is no distribution even in our modeling. Maybe we're trying to solve some online adversarial problem, and we need to give guarantees for worst case outcomes, just not a stochastic setting. And even if they do exist, even if we're willing to pretend they exist, we're generally just not going to be able to get our hands on true conditional probabilities from finite amounts of data. Like in a high-dimensional setting, I don't expect to ever see exactly the same feature vector twice. And so at time of prediction, I don't have any samples from the conditional distribution of y conditional on x that I purport to be predicting about. Of course, I could make, various parametric assumptions of varying degrees of plausibility. But if I don't want to do that, then, I just have no access to these probabilities at all because I have no samples from the corresponding distribution. Okay. But of course, people solve machine learning problems all the time. They try to predict things that, syntactically at least, look like the probability of y given x. And so what do? Well, there's sort of two things you can do here. On the one hand, you can make parametric assumptions. You can say, I believe that the world is linear, that the label is drawn from some distribution that is parameterized by a linear function of the features, and I will stick to my guns according to this belief. I'll try to estimate the parameters, and I'll give probabilities that would be correct if only my assumption was true. Or if I don't want to do that, if I'm non-parametric, then we tend to offer, instead of these conditional guarantees, we tend to offer marginal guarantees, things that are true on average over the examples. And given data, we can estimate averages pretty well. So for example, we might train a model to minimize a loss function. And we have a function that tries to predict probability of y given x, but we're not promising that we got it right point-wise. We're just promising that the squared error, or the classification error, is reasonable on average over the examples. Or if you know what conformal prediction is, maybe I'm trying to produce a prediction set or a prediction interval that contains the label 90% of the time. Of course, I don't promise that for this example. I promise that on average over the example. Or maybe I produce predictions for things like Kleiner probabilities, and I can check. I can't check whether they're right on an example by example basis, but I can check some basic things like that the predictions are unbiased, again, on average over the example. Okay, the reason we do this is because we can estimate averages. Averages are expectations over sufficiently large subsets of the distribution are things that we have access to from finite amounts of data when true conditional probabilities are not. So this is what we do. The difficulty is that once we relax things to sort of marginal guarantees like that, the true conditional probabilities were a sufficient statistic to take optimal action downstream in all sorts of decision problems, but these marginal estimates, by and large, are not. Okay, so like, I want to think about how we can make predictions that are useful for various things that we would have wanted to use the true conditional probabilities for, but that that we can actually estimate from data, or maybe get good regret bounds for in online adversarial settings. Okay. So I'm going to talk a little bit about calibration and generalizations thereof. So if you've heard about calibration, maybe it's been in sort of the context of like binary prediction or a toy problem like that, where a weatherman, we'll have a cartoon about a weatherman later, but a weatherman is like trying to predict the probability of rain every day. And you run into this problem that like you have no idea whether he was right when he said there was a 20% chance of rain today. How could you know? But like you can check not only that his predictions are unbiased, but that his predictions are unbiased in like a self-referentially consistent way. That on those days when he predicted a 20% chance of rain, it actually rained 20% of the time. More generally, what calibration asks for is that a predictor could be high dimensional, doesn't have to be predicting a one-dimensional or binary outcome. But like more generally, what calibration is going to ask for is that the prediction be statistically unbiased, that when you average over the data, the prediction, and you compare that to the average over the data of the outcome, that those should average out to the same thing, not just marginally, but conditionally on the value of the prediction itself. Okay, so this is not, true probabilities would satisfy this condition, but this is something that this is a purely statistical property that you can verify and enforce just from sort of finite samples of data. And actually, like, there's nothing especially special. Well, there's some things, but calibration is not unique. Like, you should think of calibration as asking for a particular subset of bias conditions to hold. Okay, like, think about true probabilities. If I had, real probabilities from a correct sampling distribution, then when you looked at my predictions over time, they would be unbiased, subject to any conditioning events I wanted. Real probabilities are unbiased over every subset of the outcome space. Calibrated predictions, I've asked for these predictions to be unbiased over just a modest number of specific subsets of the outcome space defined by the level sets of my own predictor. And more generally, I could ask that my predictions be unbiased, not conditional on all possible conditioning events, but conditional on some conditioning events. So, for example, if I've got some collection of events, which I will write as script E, each event, maybe for now, think of it as just sort of defined by a function that is the indicator function for that event. 1 if the event occurs, 0 if it doesn't. The event can be defined both by features that are available and by my own prediction. I might say that a predictor has E bias conditional on the events in this collection, if when I look at the difference between the average of my predictions and the average of the outcomes, conditional on any one of these events. So the vector now, this vector has low norm, ideally 0, but it has bias alpha that's less than alpha. Okay, so real probabilities, like if I was a correctly specified Bayesian, I was right about the prior, and I computed a posterior distribution conditional on all of my observations, my posterior expectation would be unbiased, subject to all possible conditioning events. But this is just asking that I be unbiased or have low bias, subject to some of them. Okay, calibration is just a special case of this, where the conditioning events happen to correspond to the level sets of my own predictor. And what I want you to think about is that, maybe there's sort of like a hierarchy of conditions that I can impose on predictions, where like the posterior expectation of a correctly specified Bayesian is sort of at the top of the hierarchy. It's unbiased, subject to like all possible conditioning events. At the bottom, I could ask that my predictor just be unbiased marginally. And in between, I could ask that my predictor be unbiased, subject to some collection of conditioning events, but perhaps not all of them. And what I want to think about then is whether there are things that I can ask for in this language, whether there are particular conditioning events that I can ask for that my predictor be unbiased subject to, such that both they're computationally and statistically tractable. I should have efficient algorithms that need only modest amounts of data that guarantee predictors that have this property, but also that they're actually useful for something downstream. And so the question is, for we could imagine looking at all of these many tasks for which the Bayesian posterior distribution on the label would be a sufficient statistic to sort of succeed in accomplishing that task, and ask for each of them, did we really need this computationally and statistically implausible assumption of perfect Bayesian knowledge, or could we accomplish the same thing with weaker conditions tailored to the task that are computationally and statistically plausible? That's the overarching question I want to interrogate, and I'll walk through maybe 3 examples in this talk. Okay, and I want to do this not in the sort of batch distributional setting, but in the online adversarial setting, which I'll define in a moment. The reason is because we can, and it's only the more general problem. If I can solve a problem in the online adversarial setting, I can also solve it via standard online to batch reduction in the batch setting, and the fewer assumptions we need to make, the better. Distributions, assuming the existence of distributions is always sort of, it's very convenient and standard, but if you think about it too hard, it's kind of tenuous, and so better to avoid it if we can. So what's the sequential prediction setting? We've got some context space X, that's where the features we get to observe before we make our predictions live. And we've got some prediction space, which for technical reasons I will assume is convex and bounded. Think about these as things like probability distributions over the set of outcomes, although they need not be. And then what's going to happen sequentially in rounds is that we, the learner, will observe some features. We will then think, and we will produce a prediction in our prediction space, like maybe we'll produce a probability distribution over 500 diagnostic codes that are relevant for some patient who's walked into our hospital. And then we'll observe the outcome. We'll learn, for example, the actual diagnosis for the patient. And our goal is that there's no distribution here, right? So how am I going to talk about like expectations and bias and all of these things that I was talking about on the previous slide? Well, there's no distribution as this process is proceeding, but at the end there is. At the end, after the t days, there is a joint empirical distribution that has been realized on my predictions and the outcome. And a goal, an intermediate goal towards producing sort of proxies for probabilities that are nevertheless useful, might be that if you give me a set of conditioning events that you care about, I should be able to promise that no matter what sequence of outcomes is actually realized by the adversary, so worst case adaptive adversary, that on the empirical distribution defined by the transcript at the end, my predictions should be unbiased in the way that we've discussed, not just marginally, but subject to the conditioning events that I've been told to care about. Okay, so it turns out you can do this. Since I want to go through applications of this kind of technology, I won't say too much about it. Let me describe the theorem to you and then maybe say just like a couple words about why you should believe it's true, and leave details of the proof for another time. So here's the theorem. So you can specify for me any collection of conditioning events that can be defined both by history and context available to me now and the prediction that I make in this round. And there is an online prediction algorithm that operates in this adversarial environment that can make predictions in d dimensions. Okay, so it's making like d-dimensional vector-valued predictions, such that if I run this for t rounds and look at the empirical bias after the fact, the worst case bias conditional on any of the events you told me to care about scales as roughly, okay, root t plus the square root of the log of the dimension times the number of events. Okay, so the, statistically, we can think about very large collections of events because the bias bound is going to scale only logarithmically, but the running time of this algorithm will be polynomial in the dimension and the number of events. And so this will be a computationally tractable algorithm only for polynomially sized collections of events. Okay. By the way, like, I mean, this sort of like the statistically optimal rate in that even if there was a distribution and we knew what it was, when we compute like empirical bias, this is kind of the deviation from zero you'd expect just by like a Chernoff bound and a union bound. And to say just like a word about like why you might believe this to be true, like here's a non-constructive argument, and then you don't have to think that much harder to get the algorithm. In any interaction against an adversary, like I can really think about me as the algorithm designer playing in an enormous zero-sum game. My strategy space is the set of all algorithms mapping transcripts of what's happened before to distributions over predictions tomorrow. The adversary's strategy space is the set of all adversary strategies mapping transcript prefixes to distributions over outcomes tomorrow. And I've got some objective, like to minimize my worst case bias. And if I want to prove a worst case bound, the adversary has some competing objective, which is to maximize it. And okay, you can like write this down and make sure you satisfy all of the conditions of the min-max theorem. But like when you realize you do, you can figure out how well you can do in this game by changing the role of play. That's what the minimax theorem tells you. What's really happening, of course, if I'm giving you an algorithm that I'm claiming to you has a worst case bound against all adversaries, is I'm committing to a strategy for the learner, the algorithm, and I am saying it does well against all strategies of the adversary, in particular their best response. The learner is going first, the adversary is responding, but the minimax theorem tells me that I can do just as well if I think about the game in the other order of play. The adversary first commits to their strategy, and then the learner gets to best respond. And if the adversary first commits to their strategy, then after any prefix of the interaction, well, I can see the prefix, I can evaluate the adversary's strategy, and so I know the true distribution over outcomes. And so one thing I could do is I could, in this order of play, predict the actual label mean, in which case I would be predicting real probabilities, and the only deviation from unbiasedness would be because of the random sampling variation, which I can control roughly like this. Okay, so it's a non-constructive argument, but you can come up with the algorithm as well by thinking about how to solve this game. Okay, but like, that's the theorem. How can we use it? And so I want to think about, okay, 3 case studies. Maybe the first is prediction for decision making. So let's say I've got a downstream decision maker. How are we going to model him? He's got some action space. That's the set of things he can do. He's got a state space. That's the labels that we're trying to predict. And for this decision maker, the state is decision relevant for him. And he's got a utility function that tells him, as a function of what action he takes and what state is actually realized, how happy he's going to be. And I'm going to assume that this utility function is linear in its second argument. If you think about the thing I'm predicting as being a probability distribution, all this means is that the decision maker wants to maximize their expected utility. Or that would be a sufficient condition because expectations are linear. Okay, so think about decision makers who would like to maximize their expected utility, which is sort of like a way you might model a risk-neutral decision maker. If you want to think about decision makers who are not risk-neutral, you need to think about other statistics other than the mean. And so just to, and of course, like the difficulty is that the decision maker needs to choose their action like before the outcome is known. So just to like maybe give a toy example, although really like, since we can handle d-dimensional states, you should think about ultimately this being most interesting for more complex examples. Suppose I've got, like a weather forecaster who's predicting the probability of different types of weather every day. And we've got someone who's maybe taking a day trip to Princeton and deciding what is the best article of clothing to bring. Okay. And you could write down some utility function which maybe gives high utility for correctly matching the weather outcome with the correct article of clothing. Okay, like this decision maker needs to think about what to do. So if the state were known, like if I knew for sure it was going to rain, then decision making would be easy. I would just, like if the state were known, then the only input to my utility function is my own action. And so I would just best respond. I would just pick the action that maximizes my utility. The difficulty, of course, is that the decision maker needs to act before the state is known. And that's where our predictions come in. Like, are we able to make predictions that are useful for this decision maker? And what I'd ideally like is that the decision maker should not need to think hard about what to do given our prediction. Like the way we should sort of, the right interface between predictions and decisions, the right API, should be that the decision maker should be able to trust our predictions and act as if they were correct. So I'm predicting something that purports to be a probability distribution over outcomes. If the thing I was predicting were real probabilities, it would be clear how the decision maker should act. They should choose the action that maximizes their expected utility over this distribution. The concern, of course, is that I'm predicting things that are not real probabilities. But what I'd like is that despite that fact, the interface between prediction and action should be the same. The right decision for the decision maker should be to treat them as if they are real probabilities and best respond. Play what would have been the expectation maximizing action. Okay, and you could imagine attaching to this constraint the question of, is the prediction trustworthy? Can I trust the prediction and act accordingly? Act as I would as if it were correct and be guaranteed against, in some sense, against some family of benchmark strategies that this is the best thing I could do. Yeah. Yeah, that's a really interesting question. And there are things you can do about that. And we can talk about it afterwards. In the guarantee I'm about to flash on the slide, we are not promising that you couldn't do better if you were paying close attention to the history. We're going to promise something weaker. There are sort of time hierarchy theorems, like essentially like, so jumping ahead a bit. Ultimately, the thing that I'm going to promise here, several slides down the road, is that if no matter what your utility function is, like, or equivalently simultaneously for all downstream decision makers, no matter their utility function, if they act in this way, I can promise them in hindsight no swap regret. Now you can think of swap regret as an extremely weak incentive compatibility condition that says, okay, like if you're limited to reacting to the suggestion, then there's nothing better you can do than to just to do it. But it's subject to sort of the criticism you raise that, well, okay, but like if we allow them to react as a function of the history, the incentive compatibility guarantee of vanilla swap regret goes away. I'm not going to talk about it here, but in general, you could think about sort of swap regret with respect to a more complex set of deviations that might be history dependent. And you get sort of time hierarchy style results. So for example, there is an algorithm that you could derive exactly in this framework that would promise that for all polynomial time functions that you could use, mapping history and my prediction to action, none of them would be beneficial compared to just following the action. But the algorithm for making predictions of that sort would not be polynomial time from like a diagonalization argument. So it is an interesting thing to sort of explore hierarchies of sort of incentive compatibility constraints like this in adversarial settings. I know some stuff about it, not everything. We can talk about it offline. Okay. And so, yeah, so like what can you do? So suppose I've got some decision makers I'm interested in. Maybe there's a lot of them. I've got their utility functions in hand. Or maybe there's one decision maker, but I don't know what his utility function is. So to be safe, I'm considering a set of them. Remember, like the technology we have in hand is we can make predictions that are unbiased, subject to some modestly sized collection of events. We want to think, like, what are the events that it would be helpful if our predictions were unbiased with respect to? And for decision makers, a helpful collection of events is defined by their best response function. The events are for each utility function and for each action, the sets of predictions that I can make that induce the decision maker, when best responding, to play that particular action. So the predictions themselves might be very high dimensional objects. The state I'm predicting might be high dimensional, and so there's a lot of them. But if the decision maker, for a single decision maker, if they have only k actions, this collection of events partitions my prediction space into only k parts. Okay, and if I've got m such decision makers with different utility functions, I have m times k many events. And so one thing I could do with the technology in hand is I could produce predictions that happen to be unbiased, conditional on the best response function of all of these decision makers. Right? These are intersecting events, so long as soon as I have more than one decision maker, but that's okay. Like we can handle intersecting events. And so when you do this, when you go through this exercise, what you find is that you can make predictions such that you can promise that for every single one of the downstream decision makers whose utility functions you had considered, if those decision makers trust the predictions and act accordingly, they just best respond to them, then in hindsight, no matter what sequence of outcomes arises, you can promise them that they have no swap regret, which means if they just do what they're told, they just best respond, the average utility that they get is at least as high as the average utility they would have gotten from any deviation strategy that had the following simple form: consider what the best response action is, and rather than playing that, play some function of that. Okay, you can't do better with respect to that class of deviations. In fact, none of the downstream decision makers can do better. And you can think about this a little bit harder, and rather than doing this only for a finite set of decision makers, you can give predictions that promise the same guarantee to all downstream decision makers, so long as they have utility functions that are bounded and linear in the predictions. Okay, so you can, in an arbitrary d-dimensional outcome space for arbitrary decision makers who are only guaranteed to have bounded linear utility functions, make predictions so that simultaneously for all possible downstream decision makers, if they just straightforwardly best respond to those predictions, they get swap regret tending to 0 at the optimal root t rate. Okay. Let's think about now a totally different application. Uncertainty quantification. So we've got all sorts of fancy machine learning these days. Like image recognition is, kind of close to being a solved problem. Like you can take a photograph and you can have a model that will tell you what's in it in a set of, 1,000 or more labels. But it's not perfect. Sometimes it makes mistakes. And if we're using these predictions to take action, especially if those actions can have negative consequences, we'd like to understand where the uncertainty lies, like how certain we are about particular predictions. If we're very certain, maybe we can sort of aggressively act to optimize our utility. If we're uncertain, especially in a decision-relevant way, maybe we should act cautiously. And one way of quantifying uncertainty that has become popular in the last few years is to produce prediction sets of labels that hopefully contain the true label with some specified probability, like 90% of the time. Okay, so ideally the sets are small. Like if I'm quite certain this is a fox squirrel, I might just say fox squirrel, that's my prediction set. But, if I was tempted to say this was a marmot, but like I'm not totally sure, maybe it's safer to list a collection of labels. And indeed, the marmot point prediction would have been wrong, but I included fox squirrel in here, so I'm okay. Okay, so that's a prediction set. Now, how do I produce a prediction set that has this semantics? Well, again, this is a problem that would be trivial if I had real probability. Okay, like maybe don't think too hard about what it means, the real probability that the image contains a marmot conditional on the pixels, but suspend disbelief for a moment and think about an actual distribution over labels. Okay, if I had a distribution over labels, and I wanted to produce the smallest set that contained the true label 90% of the time, then the solution would be just to sort the labels from highest probability to smallest. And in this sorted order, start packing them into my prediction set until I got to 90%. And that would be the smallest prediction set that had at least 90% coverage. Now, of course, if you train a neural network, it gives you things that look like probabilities. It gives you, vectors of length 1,000 if you've got 1,000 class labels that are non-negative and sum up to 1. But of course, they're not real probabilities. They look like real probabilities, but they're not. But did we need these to be real probabilities to get this coverage condition, or did we need something weaker? And so now I want you to think about a different set of events. What is the event that evaluates to 1? There's going to be one event for each label. The event that is satisfied for each label if, when I predict a particular vector of 1,000 class probabilities, the label happens to be inside the prediction set that I generate in this way. Okay, so there's an event for marmot, there's an event for fox squirrel, and it evaluates to 1 exactly when this algorithm for coming up with a prediction set contains the label, marmot or fox squirrel. So now, even though these are 1,000-dimensional vectors, in any reasonable discretization, there would be exponential in 1,000 many predictions I could make. There's only 1,000, not exponential in 1,000 conditioning events that I've specified here. And I could have other ways of coming up with prediction sets from the class probabilities. That's fine. And what you get if you ask for the predictions to be unbiased, subject to this collection of conditioning events, is that for the purposes of coming up with prediction sets that are supposed to have the right coverage probability, these are as good as probabilities. They still have the right coverage probability. You needed the probabilities to be unbiased, subject to a small collection of conditioning events, not subject to all of them. Okay, you can add on, other conditional guarantees on top of that, but maybe I want to jump to the third application just in the interest of time. I'm going to switch to slides that were produced by my PhD student, Natalie. So although all mistakes are my own fault, the visual style of the slides is about to shift dramatically. So let me tell you a story about maybe human-AI collaboration. If you want to design a predictive algorithm that is going to help a doctor in some diagnostic task. Okay, so we've got a patient who arrives, and there are features relevant to this patient, maybe some of which are legible to both the machine learning model and to the doctor. But like there's other features that are legible only to one of them. So maybe the doctor can sort of make qualitative observations. The doctor can sort of look at the patient's, get a sense for the patient's disposition. They seem a little grumpy. You can poke them and see what noises they make. You can smell them. Okay, these are all things that might be useful for the doctor in some hard to specify way, but would be like tricky to like encode in a way that you could like input it to the neural network. On the other hand, the neural network has information the doctor like can't really internalize. It was trained on millions of patient records, and that's not something that you can just like easily feed to the doctor. And so, like the neural network, which is, predicting something, comes out with some prediction. Maybe this is even like a really good model, right? Like maybe we've gotten really good at predictive medicine, but even if it's better than the doctor on average, like because the doctor has access to information that the model doesn't, there are times when the doctor ought not to agree with this estimate, and because they've got information the model doesn't have. And so maybe the doctor is unhappy, changed from happy to unhappy there. Okay, and the doctor disagrees. And so like what we would like is, so at this point, what's the doctor going to do? He'd like essentially follow the recommendation of the model, or they could say, I don't think the model's right here. I'm going to go with my gut. I'm going to do my own thing. But what would be better is if they could interact in some way, have a conversation, and internalize the information that both of them had and come to a better treatment decision for the patient. Okay. So having told this story, you might think to yourself, oh, I remember something that might be useful here. It's called Oman's agreement theorem. This is sort of a classical theorem about Bayesians. It's a theorem about Bayesians with correctly specified priors. In particular, it says if I've got two Bayesians who share a common prior over patients, and they're correct about that prior, like it's correctly specified, the patients really are sampled from that distribution, and we have common knowledge of each other's posterior, meaning, I know that you know that I know that you know that I know what my belief is, and iterated infinitely, then we have to have the same posterior. Bayesians with common knowledge of each other's posteriors cannot agree to disagree. We don't need to share the information we have about the patient. That might be hard to do, because how do you tell the model exactly what the patient smells like? We just need to know each other's beliefs, but in this strong sense. We need to have common knowledge of each other's beliefs. Then we actually can't disagree. That's Ullmann's agreement theorem. Now, common knowledge is sort of like a fixed point kind of thing, but like it's been known for a while that actually this kind of agreement can be reached constructively, at least if there's a finite number of ground states. It's been known for since 1982 that if we just engage in a conversation in which we exchange our beliefs, I think the risk is X. You tell me, oh, well, updating based on what you just told me, I now think the risk is Y. We go back and forth. We will in finite time agree. And in fact, Scott Aronson proved in 2005 that at least in the special case of one-dimensional expectation, so if we're arguing about the probability of some event, then if we don't care about exact agreement, if we just want our probability estimates to be within epsilon of one another, then with probability 1 minus delta over the draw from the prior, if we engage in a conversation if we engage in a conversation, we will come to epsilon agreement after at most 1 over epsilon squared delta many rounds. Okay. The nice thing about this theorem is it is independent of the complexity of the distribution, right? I might be observing really high dimensional covariates, as might you. The interaction between those and the posterior distribution on Y can be like arbitrarily complicated, still 1 over epsilon squared delta. Okay, so like we could engage in this conversation, say epsilon is 0.02, the computer tells me the risk is 0.2, I say it's 0.4, the computer updates and says it's 0.34, I say it's 0.32, 0.32 and 0.34 are within 0.02 of one another, we're done, we've agreed quickly. Okay, So that's a nice story, but like, it has some difficulties. It assumes we have a common prior. Why do we have any prior at all that is correctly specified, let alone the same one? It also assumes that we have access. I mean, all of this is ultimately assuming we have access to real probability, that we have a correctly specified prior, and that we are able to compute correct posterior beliefs, not just conditional on the evidence that we've seen, but conditional on the transcript of this conversation we've had, which involves integrating over all possible observations that might have led you to the same belief. Okay, so it's computationally intractable. And it's a stretch to assume this of the doctor, but maybe even worse, like you're on the hook for implementing this for the model if you want to like appeal to Oman's agreement theorem, and you're going to have a hard time doing it. It's unclear how this theorem is going to generalize beyond one-dimensional expectations. Like really, a medical setting, we probably want to be talking about distributions over, all possible diagnoses. And so the question is, can we relax these assumptions and that sort of assume we really know real probabilities to something that is tractable? Okay, and the answer is going to be yes, with conditional calibration subject to the right set of conditioning events. So here's the kind of, here are the conditioning events, and it's going to be something that I'm going to call conversation calibration. And conversation calibration will be something that if we were in the classic Omanian setting in which there were Bayesians that really had a correct prior and could perform correct posterior updates, they would satisfy this condition. Okay, so I'm going to be writing down a strictly weaker condition. It's only going to generalize Bayesian decision makers, but it'll have the sort of not insignificant advantage that it will be computationally and statistically tractable, even in adversarial settings. We can write down actual algorithms that will guarantee this with good rates of convergence, even if there is no distribution. Okay, and it will imply in the one-dimensional setting exactly the same convergence theorem, this sort of 1 over epsilon squared delta rate of convergence that follows from Aronson's result in the actual Bayesian setting, but under these much weaker assumptions. And it'll generalize to beyond the one-dimensional setting. We can be talking about distributions over 1,000-dimensional vectors, all possible diagnoses. And in fact, we don't need to specify those distributions in our conversation. We can have our conversation just about actions. We can talk about treatments rather than beliefs. Okay. So calibration. Again, maybe think about like a weather forecaster. It's hard to know when she predicts a 70% chance of rain, whether she's right on that particular day. But over a long sequence of predictions, I can interrogate like when she predicted a 70% chance of rain, did it rain 70% of the time? Okay, yes, it did. And I can interrogate that for her other prediction. When she predicted a 20% chance of rain, did it rain 20% of the time? No, it didn't. She's not calibrated. We've falsified the hypothesis that she's predicting correct probabilities. And so now I want to imagine agreement in this online adversarial setting that takes place over time. I'm going to draw you a picture here that has 2 axes. So every day, a new patient arrives and has features that are legible to the human being and the machine. Then on that day, the machine and the human being have a conversation that takes place over rounds. The columns are days, patients correspond to columns. Rounds of conversation are rows. Okay, and each conversation proceeds until agreement. And then the next patient arrives the next day, and again, we have a conversation that proceeds until agreement. Okay, and so time proceeds, and we fill out this table, and we've got, again, every day a new patient, and then rounds of conversation. So the condition that I want to ask for, that I'm going to call conversation calibration, is sort of, I'm going to say, okay, I want that at every round of conversation, the predictions that I've made at that round, viewed as a sequence over the days, should be calibrated, not just marginally, but conditionally on what the other guy said at the previous round. Not conditionally on the whole conversation. That would be too many conditioning events. Just conditioned on what was said at the previous round. So for example, subject to some bucketing, I might look at all of the rounds at which my interlocutor at the previous round said something close to 0.1. That selects out a subsequence of my predictions, and I would like that subsequence to be calibrated to the outcome. That's conversation calibration. And that should hold for every round of conversation, but the crucial thing is I'm conditioning only on what was said at the previous round. So it's a small number of conditioning events. Okay, so it's just some conditional calibration guarantee. It just says that I want my predictions to be unbiased, conditional on a modest number of events. But the kind of thing that we can guarantee in online adversarial setting. And it turns out this is enough to recover agreement with the same parameters as before. How come? Well, think about some particular round. There's sort of two things that can happen in the round when I make my prediction. It could be that on most of the days, I actually agree. I make a prediction that was the same or close to the prediction made at the previous round. That's a good case for me because I'm trying to argue that these conversations don't go on for too long. Or if that didn't happen, it must have been on most of the days I made a prediction that disagreed substantially from what my interlocutor said yesterday. But I was calibrated conditional on what he said yesterday. That means that, for example, if I look at the subsequence of rounds for which my interlocutor predicted 0.1 and I predicted 0.3, on that subsequence of rounds, the outcome was 0.3 because I'm unbiased, subject to that conditioning event. Which means that my squared error on those predictions is substantially lower than the squared error of my interlocutor. Which means that if I did not agree on most of the rounds, on most of the days at round 10 of conversation, then when we look at the squared error of my predictions at round 10, it's substantially lower than the squared error at round 9. So every day when I don't agree on, every round when I don't agree on most of the days, I have to get substantially more accurate, which is good. The conversation's useful. And squared error just can't decrease substantially too many times in a row because it can't go below 0, which means that we have to converge quickly. And so, okay, you recover quantitatively the same 1 over epsilon squared delta convergence theorem. Now it's in this frequentist setting. There's no prior. So we're saying for arbitrary sequences of patients, for a 1 minus delta fraction of patients, the conversation ends after 1 over epsilon squared delta many rounds. Of course, if you did want to assume that everyone was Bayesian, because Bayesians would satisfy this calibration condition, all of the theorems here lift to the Bayesian setting, in the single shot setting. How come? Because I could just conduct a thought experiment. I could say, okay, I've got a patient in front of me. I'm going to have a conversation about them. I'm also going to just imagine that a zillion more patients come after him, and I'll have conversations about them as well. In my imagined version, they're all drawn from the same common prior. Because we're Bayesian, we would satisfy these calibration conditions to arbitrary precision as time went on. And because we're Bayesians and the examples were IID, the conversations would be statistically independent of one another. They'd be permutation invariant. And so in particular, we would agree on round 1 with probability 1 minus delta. So I didn't actually need to conduct these hypothetical conversations. Okay, and then, yeah. Both of them need to be conversation calibrated, which is a much weaker condition than Bayesian rationality, but it's also enforceable. So if you were worried that the doctor might not be conversation calibrated, I can produce an algorithm, think of it as a megaphone that he can speak into. The things he utters into it are just his judgments. The things that come out the other end are conversation calibrated and are only more accurate than the things he said, have only lower squared error. So it's we need both parties to be conversation calibrated, but if they're not, it's an easy condition to enforce. And you can enforce this on any model. So you can, on your end, you can start with whatever is your favorite trained neural network and then turn it into a protocol that can be conversation. Okay. And then I won't tell you about it because I'm out of time, but we were speaking as if we were having conversations about one-dimensional expectations, which is sort of what the prior literature talked about. That's kind of a toy case. Like, presumably the payoff relevant state is some high-dimensional object, like distributions over all possible diseases you might have. And nobody's gonna, like, we can algorithmically make predictions over high-dimensional objects, but the doctor's probably not gonna want to engage you in conversation in that language. But we can talk about decision calibration. And this is going to allow us basically to conduct the conversation in terms of best response action. If we imagine that the person we're talking to has a utility function, mapping actions that they take and states to payoffs, the conversation can take place in terms of what we believe is the best response action. So rather than numeric valued vectors, the conversation can proceed as, I think you should amputate the left arm. Now that you've said that, I think you should amputate the right arm. And then we both agree to prescribe ibuprofen. All right, so thank you for having the patience to listen to this. The stuff I talked about is in a series of 3 papers. The decision stuff was in EC last year, and the agreement stuff is going to be in the upcoming stock. Thanks.
So this reminds me like in history, in poker games, they play with your friends and you have some information and
yeah, so like extensive form games are like examples of games that have very large strategy spaces. So one thing you can do with this technology is you can, okay, you can't quite get no swap regret in extensive form games, but you can get no conditional regret subject to any polynomial number of conditioning events. So regular external regret is like a marginal guarantee. Says I do as well as I could have done in hindsight with the best fixed action as averaged over all of the rounds. Swap regret is like a bunch of conditional guarantees, one conditioned on each action you take. It's too many if the action space of the game is exponentially large. But what you can do with this technology is you can, in an extensive form game, give no regret, not just marginally, but subject to any polynomial number of conditioning. All right, thanks.